All right, picture this. You've got a spreadsheet or a database table with thousands, maybe even millions of rows of data. All the raw information is there, sure, but the story, it's completely buried. So how do you find it? Well, that's exactly the power we're going to unlock today. We're going to see how SQL aggregation can turn that overwhelming wall of data into just a handful of really powerful insights. To see how this all works, we're going to use this simple little student table. It's got an ID, last name, faculty, and GPA for each student. Now, it's great for looking up individual details, but it's not so great for seeing the big picture, you know? But here's where it gets tricky. With just 6 rows, we can just look at it. No problem. But what if there were 6 million rows? You can't just scroll through all that. How do you answer big picture questions like, what's the average GPA for the whole university? Or exactly how many students do we have? That's the problem we're here to solve. So how do we start to tackle this mountain of data? Well, we need the right tools for the job. We're going to start with 5 foundational functions. Think of them like data summarizing superheroes, each one capable of squishing millions of rows down into a single powerful number. These tools are called aggregate functions, and the best way to think of them is like a data compressor. See, a normal function works on just one row at a time, like maybe capitalizing a single name. But an aggregate function is totally different. It takes a whole bunch of rows, all at once, and collapses them down into one single summary value. Let's kick things off with the simplest one of all, count. Its job is to answer one very basic question: how many? So if we want to know the total number of students in our university, we just ask SQL to count up all the rows. And boom, just like that. It takes our 6 rows and gives us back a single number, 6. We've just done our first, most basic act of summarization. Instead of 6 pieces of info, we now just have 1. But count is actually a lot more clever than it looks. Count star gives you the grand total of everything, but if you use count faculty ID, it's smart enough to ignore any students who don't have a faculty assigned. And count distinct faculty ID is even cooler. It tells you exactly how many unique faculties we have in our entire data set. Pretty handy, right? Next up, let's bring in the arithmetic power tools, sum and AVG, which, of course, stands for average. If you've got a column of numbers, sum will add them all up, and AVG will, well, calculate the average. These are going to be your go-to functions for pretty much any kind of financial or statistical number crunching. So, for example, we can calculate the average GPA for the entire university, which turns out to be 4.25. And just like that, we've boiled down 6 different GPAs into one singular, meaningful statistic. That is aggregation in action. Okay, rounding out our basic toolkit, we have MIN and MAX. These are for finding the extremes, the absolute highest and lowest points in your data. And what's really cool about these is they don't just work on numbers. They work on text and dates too. So we can easily find the highest GPA, 4.8, and the lowest, 3.7. But check this out. If we use min on the last name column, it finds the first name alphabetically, Bondar. That kind of flexibility makes these functions incredibly powerful. So we have these 5 really powerful tools. We can find the average for the whole university, no problem. But what happens when we try to ask a slightly more complex question? Well, we run smack into a major roadblock. It's a logical contradiction that SQL just can't figure out on its own. Here's the problem. If we ask SQL to show us the last name and the AVG of GPA at the same time, it gets confused. See, the last name column has 6 different values, one for each student. But the AVG of GPA function returns only one value, the average for everyone. So which of the 6 names should it put next to that one average? It's a paradox, and your query will just fail. And this question right here gets us to the real heart of data analysis. We don't just want one big grand total. We want subtotals. We need to answer questions like this one. What's the average GPA, not for the whole university, but for each individual faculty? How in the world do we do that? The answer lies in 2 simple words that completely change the game for how aggregate functions work. It's time to unlock the real power of group by. Okay, so here's the magic of group by. It basically tells the database, hey, before you do any of that summarizing, I want you to first sort all the rows into little buckets. All the rows that have the same value in a column, like the same faculty ID. They all go into the same bucket. Then, and only then, does it run those aggregate functions on each little bucket one by one. And the result It's an absolute game changer. Instead of one summary for the whole table, we get a nice, clean summary for each group. We can see, clear as day, that Faculty 1 has 3 students with an average GPA of 4.23, while Faculty 2 has 2 students with a 4.35 average. We've solved the paradox, and we've unlocked a much, much deeper level of insight. Okay, this is great. So now we can create these powerful summary groups. But this just creates a new question, doesn't it? What if we want to filter the groups themselves? Not the individual rows we started with, but the final summarized results. So, imagine your dean comes to you with a request. They only want to see the data for the large faculties, the ones that have more than 2 students. Now, this seems simple enough, but our existing tools, well, they're not going to work here. Your first instinct is probably to use the where clause, right? Makes sense. But if you try something like where count star greater than 2, your query is going to fail. And here's why. It's all about the order of operations. SQL uses the where clause to filter out individual rows before it does any of the grouping. At that stage, the count per faculty doesn't even exist yet. You can't filter on a number that hasn't even been calculated. Here's a really simple way to think about it. First, SQL gets the data. Second, the where clause filters those raw rows. It's only then, in step 3, that group by creates our summary buckets. So to filter those buckets, we need a new tool that works later in the process, at step 4. And that tool is having. This is the one thing you absolutely have to remember. Where filters rows. Having filters groups. Where works on the raw individual data before you do any summarizing. Having works on the aggregated, summarized results after the grouping is done. They do a similar job, but at totally different stages of the query. And here it is, the final correct answer to the dean's question. By using having count star 2, we're telling SQL to first group everything up, then calculate the student count for each group, and then, finally, to throw away any of those groups that don't meet our criteria. And we're left with just Faculty 1, which has 30 students. Perfect.
So, we took a really simple student table, and we managed to pull out a powerful filtered summary. But this is universal. Just think about the possibilities here. You could group sales by region to find your top-performing markets. You could group website clicks by country to understand your audience. You could even group system errors by the hour to find out when things are most likely to break. Just remember, the raw data is only the starting point. The real story, the real insight is always found in the groups.